Hi, my name is James Birchall and I'm currently a PhD student here at the University of Bristol, and I'm going to talk to you over the next few minutes about the topic of my research, which is machine-to-machine communications over 4G networks. We'll have an intro of machine-to-machine communications first, but we'll be back in the lab soon enough to have a look at how this equipment works. Let's take a look at what machine-to-machine communications are. These are generally technologies that allow devices to exchange information with each other without the manual assistance of people. Some examples we have shown here on the screen. To begin with, wireless sensor networks. These are generally groups of remote sensor nodes that can communicate with each other and back to a hub where they can send data to be analysed, for example, monitoring river levels in flood-prone areas. Asset tracking, another common use. For example, if you own a fleet of expensive vehicles, it's of a lot of benefit to you to be able to track these, see whereabouts they are, and be able to monitor their locations in the event they're stolen. Similarly, security is a popular use. We can place wireless video cameras in remote locations where they wouldn't ordinarily be able to communicate back to the customer and keep track of more static assets. Finally, healthcare. This is a really important up-and-coming use here. We can use sensors that are attached to people who are perhaps vulnerable or elderly and keep an eye on them, so if they fall or have an accident, the appropriate emergency services can be summoned. Let's take a look at cellular communications and how they work. At the top we see a traditional architecture. We have the mobile phone. This communicates with a base station, which typically will be quite close to you but can be anywhere up to 35 kilometers away. This can then use a backbone communications link to communicate with a web server, so information will flow from right to left in this case. The bottom image shows more of a machine-to-machine type architecture where we've used Raspberry Pis and a 4G modem together with a base station emulator. This will be explained in more detail in the laboratory video. As you can see here, we've used a Raspberry Pi, a U-Blox modem to connect to the network, and a Keysight base station emulator. The block diagram here shows the flow of data through the system. This is generated by the Raspberry Pi, transmitted by the modem, received by the base station emulator, which then passes this on to a Raspberry Pi server. It's worth noting that the RF signals between the modem and the emulator are bidirectional in order to allow the modem to negotiate for resources and receive acknowledgements from the base station. From this block diagram we see the two main parameters we want to record. Firstly, we want to record the DC power consumed by the 4G modem, and this is the total amount of energy used during all of the operations that occur within this. Secondly, we also want to look at the RF power. This is the wireless power transmitted from the modem and can vary depending on a wide variety of factors. Let's take a look at some of the equipment we have set up in the lab. As per our block diagram, we have our Raspberry Pi here to generate our data. This is then transmitted with our 4G modem. The RF portion is received by the base station emulator, and this data is acknowledged with our Raspberry Pi server over here. To keep an eye on the signal, we can use our high-speed oscilloscope, and we also have some additional circuitry here to monitor DC power consumption and the RF envelope. Here we see the interface on the Raspberry Pi. We have two scripts here. The one on the left, which we're just about to run, configures the modem and sets up the IP interface so the Raspberry Pi can transmit data via the modem. Once this is configured, we use the script on the right, which simply sets up a UDP socket and allows the data to be transmitted from one Raspberry Pi over the 4G network to the one on the other side. Here we see the interface on the base station emulator. We'll look at some of the spectrum analyzer functionalities which allow us to visualize the data being transmitted by the modem. Here we see a spectral plot which allows us to measure the power transmitted in the channel. Next we can see the constellation diagram which illustrates to us the modulation schemes being used by the modem. In pink we can see here the 16 QAM modulation scheme which transmits the useful data. And we can also see in green the Zadov-Chu sequence, which is used to demodulate the signal at the base station. One interesting aspect we can see here is the error vector magnitude, or EVM. We can see this is manifested by the slight scattering around the 16 QAM data points. This is also shown as a measurement on the right-hand side of the screen. Here we see a map plot of the resources available to the modem. The y-axis shows the data symbols, which is akin to the time domain, and the x-axis shows the resource blocks, which is like the frequency domain. Similarly to the previous constellation diagram, the pink shows the data transmitted from our Raspberry Pi, where the green is the demodulation reference signals used by the base station. This clip shows the interface from our high-speed oscilloscope. We can clearly see here our modulated RF signal. Our sampling rate is actually sufficient that when we zoom into the signal, we can see the carrier wave in real time. In order to measure DC power, we use a system represented by the schematic on screen now. This is quite a basic system where we use a low value sensing resistor to measure the current. As with Ohm's law, we should see a small voltage drop over this resistor, which will be proportional to the amount of current used by the modem. This is then amplified by a differential amplifier before being fed into a high-speed analog to digital converter, which will enable the signals to be logged on a laptop. The supply voltage is also measured in the same way. The signal coming in here is a trace from our modem waking up and transmitting a single packet of data. This video is from our LabVIEW interface, which enables the signals to be recorded and stored for later analysis. The three traces shown on screen are white, which is supply voltage to the modem, red, which is our current consumption, and green, which is the magnitude of our RF envelope, or the signals we transmit wirelessly. Taking a closer look at this trace, we can see the signals start to peak when our modem initializes its USB interface and begins to wake up its baseband processors. Current consumption then peaks when our green trace peaks as well, and this is when the modem speaks to our base station, registers on the network, and asks for resources in order to transmit a signal. There's quite a long pause in the middle, which has been artificially put in to enable us to separate out the signals going on, and then we can see right at the end of the trace we transmit our little packets of data over the network and then go back to sleep. So what's the point in all of this? How can we use the information we record? Well, in the most basic state, we can start to form models of how the modem operates. We can see how the power consumption varies with the amount of power it needs to produce, and also the data rate at which we wish to send the data. More importantly than this, we can start to use these models in order to optimize our communication systems in order to make them as efficient as possible. For example, is it better to transmit small packets of data regularly, or wait until the end of the day and send a large stream of data? In addition to this, we can do some really interesting analysis of the wireless signals transmitted, and we can see if we can improve the hardware in order to further improve efficiency. For example, can we produce an intelligent power supply for the RF power amplifier that would drive this efficiency as high as possible with minimum computational overheads? Thanks very much for your time. I hope this video was interesting for you, and I look forward to posting up more with any further research outcomes.